Okay, so let's go ahead and start with 6.2 here, volume using cylindrical shells. So it's another method here when you've got something that you can essentially fit in concentric cylinders inside. And then we can do this. So looking at this, we're going to do an example here with an axis of revolution back at -1, and we're going to revolve around y equals 3x minus x squared. And you can see that function right there. All right, so let's go ahead and do that. Our axis of revolution is going to be back here at -1. And so right here, you can see the shape that it's going to revolve into. Kind of like one of those, is it a bundt cake? Is that what that looks like to me? So, you know what I'm talking about? One of those cakes that you cook in the thing, and then they flip it over and it's shaped like that. Yeah, so that's what it looks like to me. And so you can see here in this picture, we can fit inside of it cylinders, right? If you look right at that one, you can see inside of that is cylinders, and we could fit in other concentric cylinders, right? You could go back over here, draw in a cylinder just like this, and we would have another cylinder right there. So we can fit in concentric, you know, cylinders like this. Right? You can fit in these other cylinders. And so if we can find the volume of these thin-walled cylinders and add them all up, then we can do this. So that's what we're going to look into doing here, is finding these cylinder volumes. If we look down here, there's an outer and inner radius for this, which we'll worry about here. But if we cut it along this line and roll out the cylinder, we essentially get like some sort of a rectangular cube shape there, right? And we can see then that we're going to have a height equal to some difference in, you know, whatever we're changing that our height is. And then we're going to have a thickness that's essentially the circumference of that cylinder, or not the thickness, this length here. This is essentially the circumference of it. And then we have a certain thickness to it for how big of a change in that x we took for how thick we made it. So if we come back over here, if I wanted to find the volume of that slab, once we took that cylinder and rolled it out, how would I find the volume of it? Nope. Just in general, I have a rectangular shaped thing that's got a box, essentially. How do I find that volume? Okay. There we go. So the base times the width gives us the area, and then times the height. So we would just essentially, if we're looking at all these, we want the length of it times the height of it times the width of it, right? How thick it is. The length of it is going to be the circumference. Okay, that's the circumference. That's this down here. This is circumference. Circumference of the circle. The height of it is simply our f of x value, right? Because when we look in here, the height here is y, which is just whatever f of x happens to be, f of x sub k. Right there, or whatever x value we've chosen there. I got bad. There we go. F of x sub k right there. That's going to be the height of it. So this is times our specific f of x. That's our y value, right? Our height at that point. And then times whatever thickness we're doing, delta x, how big of a step we took between the outer and inner wall in x, right? So, you know, if we're looking in here and we look at this little inner wall right here, that's delta x. That's how thick it is, correct? You all agree with that? And that's how big of a step we took between, consecutive x's we're looking at. So to find this is 2 pi r. That's our circumference. This is still f of x. This is still delta x. The radius, what's the radius going to be? Go up to this picture for that. So if we're looking, say our cylinder wall is right here, right? What's our radius for where we're revolving around? In other words, in this picture, we're looking at like, say, right here, right? What's our cylinder radius when we draw in this cylinder? Yeah, there you go. We've got, this is our radius r here, right? Correct? And so it's going to be, this is the value for x we're plugging in. This is -1. Correct? So we want to do, come back down here, for our radius, we want 2 pi times x minus whatever our axis of revolution is here, which in this case is -1. So it'd be minus -1, right? We'd have a minus -1, which would give us whatever. So if x was 2, we'd have 2 minus -1. That gives us a radius of 3 for that specific shell, that specific cylinder. With me so far? Isn't it neat how this just works out from geometry, right? And I know some of y'all are taking geometry, so you should be very happy about that. Okay. Then we still have times our function times delta x. So that right there, there's our volume, which means we now just need to go in and actually add up all these volumes, right? That's the volume of a single specifically chosen cylinder or cylindrical thin-walled cylinder. So now let's do this to integrate it all up. So that's the volume of of the, let's call it the kth one, sub k, whatever these things were, right? Sub k. And then what we're going to do is the total volume, right? And then that's going to be, we're going to integrate from, where were we going in y? Or I'm sorry, not where are we going in y? Where are we going in x? We're starting with our first cylinder here, out down here at 0, cylinder, 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 all the way up to 3. Good. So 0 to 3. 0 to 3. And then we've got our 2 pi. We've got our x minus our axis of revolution, which could just be 0, right? It's just shifting our graph, essentially, right? You could think of it that way, as just shifting, right? That -1 is a shift to the right. So we essentially could just take this graph, shift it 1 to the right, and then rotate it. And we'd have the same shape, just at a different location, which would give us the same value. So whichever way you prefer to think about it. Minus the axis rotation, or just shifting your graph over so that it's back. In other words, you're shifting it over so it's back to rotating around the y-axis rather than something else. Whichever, same result, different way of thinking of it. All right. Then we need times f of x. So what was our function here? Yep, there you go. 3x minus x squared. So times 3x minus x squared. And then how big of a step are we taking? What's our thickness? dx. Brilliant. dx. Okay. That's pretty cool, right? We can use geometry to set up this calculus stuff. I've always thought that was so neat. Some of you kind of do. Some of you feel obligated to say yes. Oh, there you go. So this is going to be, I can bring the 2 pi out front, 0 to 3. This becomes x plus 1 times our 3x minus x squared dx. We can multiply those together. 2 pi 0 to 3. My handwriting's getting messy because I'm not taking my time. Sorry. 0 to 3. This is 3x squared, and then minus an x cubed, and then plus a 3x, and then minus an x squared dx. So this becomes just a 2x squared, right? Dx. Does that look right? 3x, 2x squared minus x cubed plus 3x. Yeah, I got that before. So, and then we just start integrating. So this is 2 pi. 2x squared becomes 2/3 x cubed minus x to the 4th over 4 plus 3x squared over 2, evaluated from 0 to 3. I'm running out of room here. Plug those numbers in. I think I can do it here. We'll end up with 2 pi times, what do we got? 3 cubed is 27 times 2 is 54 over 3 minus 3 to the 4th is 27 times 3. What is that? 70, 81, right? 81 over 4. And then 3 to the 3rd again is that plus 27 over 2. And then minus zeros. So I don't need to write those, right? Those are all going to be zeros. And then you can go through and do this, whatever this is. This is going to be ... Do your algebra, I'll let you practice those. You can reduce the 54 over 3. Not the 81 over 4 though, huh? So, but 54 can be divided by 3, right? That's 10, 18. So you could do 18 times 4 over 4. And then, what is that, 72? 72 minus 81. What is that? That's -9. That's, and then -9 plus 54. 45. And then 45 times 2. Did I miss something? That's a different answer than I have. But then it's over 4. So it's 90 pi over 4, which is 45 pi over 2. There we go. Woohoo! That's the answer I got before, but I did it in a slightly different way. Isn't that funny that you do the same problem multiple times, like every time you do it slightly differently? Wonder why that is. Wonder why you even think through the exact same way every time. Yeah. Every time I solve them, I always end up doing them slightly different ways, thinking of them differently. So only occasionally does it ever match what I have in here before I get to the answer. Any questions on that? Yeah, it's recording. Now you're talking through it though. But... All right, so what we just got from that last one was ultimately V equals whatever it is, 0 to b of 2 pi times our shell radius times our shell height times dx, which ultimately was not 0 to b, a to b of 2 pi x minus L, which is our line of our vertical line that we're rotating about, times our function, which was our height, times dx. So that's what we got there. Okay, that's what we just came up with when we did that last problem, just based on figuring it out, right? We didn't even, but now that's ultimately what it gave us and what we did, correct? All right, and so then this should continue working. So let's look example 2 here. The region bound by the curve y equals the square root of x, the x-axis and the line y equals 4, or x equals 4, sorry, is revolved about the y-axis to generate a solid. Find the volume of the solid. So we're revolving it around the y-axis, which means L is going to be 0. We don't have to actually do anything with that. We don't have to do any shifting or anything like that. And so we're going to go through here and try and do it. So first off, what are our limits of integration here? How do you know that? If it wasn't on the graph. Well, that's our heights. But we're revolving it around the y-axis, and so that's where our graph starts. We're looking at above 0 here, right? So if we look at our graph, it starts here at 0, and then it goes out to x equals 4. So that's where we're stopping. If it was x equals 5, we'd go 0 to 5. 0, x equals 100, we go 0 to 100. So it's just how far are we moving along the x-axis, and we're going from 0 to 4 there. Okay? So 0 to 4, it's from the y-axis out to that 4. So limits of integration, 0 to 4. So let's do our volume here. Volume equals integral from 0 to 4. We need our 2 pi. Then we need x, right? Because that's our what? That's our radius. And we're not shifting it, so we don't have any minus L or anything like that. That's just our radius is x. So at every point on here, this is our radius, r equals x. Then we need times our height. What's the height here going to be? Yep, it's our function, right? This is our height, h here. This is h. So this is going to be square root of x, which is f of x, right? And then we need our thickness, dx. How about that? So this becomes 2 pi, 0 to 4. What do I write inside here? Let's combine that into 1x. X to the what? Nope. There we go. This is x to the first. This is x to the 1/2. What's 1 plus 1/2? Well, that's 2 over 2 plus 1/2. That's 3/2. So it's x to the 3/2, right? And then dx. I'll leave that line then. So then this becomes 2 pi square root 0 to 4 x to the 3/2 dx. What's the integral of x to the 3/2? Or the antiderivative of it? Right, add 1, then divide by the 5 over 2, which becomes times 2/5. And this is from 0 to 4. So this is 2 pi times, and here we can even bring out the 2/5 if we want. This is 2 pi times 2/5 times, and this will be x to the 5/2. So this is going to be 4 to the 5/2, right? I don't need the over 5 anymore. So 4 to the 5/2 minus 0 to the 5/2. So what's 4 to the 5/2? Well, we can do the square root of 4 and then put it to the 5th power, or we can put 4 to the 5th power and take the square root. Square root of 4 is pretty easy, right? You can do it in either order, right? Like I can say 4 to the 1/2 to the 5th equals 4 to the 5th to the 1/2, correct? So I can pick my order. I think that order is easier because the square root of 4 is just 2. And then 2 to the 5th is, I think Truman knew this one the other day, yesterday. Thanks, Truman. Good. So this becomes 4 pi over 5 times 32. And 32 times 4 is what? Well, yes, 300. Well, what's 4 times 30? 120 plus 4 times 2. 128 pi over 5. Boo-yah. Cool, huh? And I guess you could make that times a pi or times an e, right? Not really if you're listening to the recording. Little inside joke. Don't swap the pi for an e. Don't do that. All right, any questions on that one? No? Okay. Next page. Let's take a look at this one, example 3. So I've done a few of these with you. Go for it. How much time do we have left? 12:37? Okay. That's all you.